Okay, so hello everybody, I'm Ruadhan, and this video is just a quick follow-up to the recent discussion about the Rodin number map and relativistic wave equations. And there have been some people who've been saying that Mod 9 isn't special, and I just wanted to address why these people are saying that and in what way it is special and in what way it isn't. So let's first look at why people are saying that it's not special by looking at what I think is going through their minds when they look at the Rodin number map and they see talk about relativity, quantum mechanics, field theories, and Mod 9. So what's not happening, this is something you can do, but it's not what we're doing. If you have a field, physical field, that takes different values at different locations in space and time, and if those are integer or rational values, then you can reduce those values mod 9 and you can get a unique digit in between 1 and 8. And you can imagine tiling of space and time with these digits between 1 and 8. Say, for example, it could be electrical potential, and instead, wherever there's, say, 10 volts, you could treat that as though it was 1 volt. You could do that, and you would get a sequence of digits covering space-time, and you could look at the dynamics of those digits, and it would be, in a sense, it would obey certain equations, and it would give a kind of a slice of the full dynamics of the electrical field. But the thing is that Mod 9 is not actually special in that way. You can do that with Mod 11, you can do it with any modulus, and that's not actually what we're doing. And if it doesn't actually, although you can do that, it doesn't make a lot of sense to do that. It would be like, for example, if you could take your bank balance mod 9 and say, for example, that could be 7, and something you wanted to purchase, its price mod 9 could be 3. And then if you bought that item, the balance in your bank would change from 7 mod 9 to 4 mod 9. So if you can do that, you could keep track of some aspect of your finances that way, but it's not very informative and it's not very useful. And it's similarly not useful to treat 10 volts as though it's the same as 1 volt. So that's not what we're doing, and that's not the way in which we're using Mod 9. What we are doing is we're using Mod 9 because it describes the structure of 3 plus 1 dimensional spacetime, and I'll explain why that is. So it has to do with groups. So a group, this is the definition of a group. It may be familiar, but I'll go through it anyway. A group is a set with an operation that combines any two elements to produce a third element in the same set, and the operation has to be associative. So if you combine A with the result of combining B and C, then you get the same thing as if you combine A and B and then combine the result of that with C. There's an identity element, E, such that any element combined with the identity element gives you the original element. So A combined with E or E combined with A gives you A for every element A. And every element has an inverse. That is an element that when you combine it with that element, then you get the identity element. So the simplest example of this is the integers. If you have two integers, you can combine them together by adding. And there's an identity element which is 0. If you add it to anything, it doesn't change. And every integer has an inverse, an additive inverse. So if you have minus n and then you add it to n, then you get the identity element, which is 0. So that satisfies the definition of a group. So the integers are a group under addition. And the integers are an infinite group, of course, but and here we're going to be looking at finite groups, and specifically we're going to be looking at cyclical groups. So the cyclic group Zn, which is the integers mod n, it contains n elements, all of the positive integers and that are less than n and 0. 0 is the identity element, just like it is with the integers, and addition is defined modulo n. So if you add 1 to n minus 1, then you get 0. So it wraps around, and this is why it's called a cyclic group. So now we come to chromatic groups, and this is really the central concept of the video. So it's worth going through the definition. I'll read it out and then go through it more carefully to make sure that everything is clear. So given an n plus m dimensional spacetime, so you have n space dimensions and m time dimensions, the chromatic group of that spacetime is a finite group with an odd number of elements that naturally generates a labeling of the spacetime, which assigns a label to each cell that differs from the labels assigned to all the neighboring cells, and all the labels assigned to the neighboring cells are different from each other, and it uses all the non-identity elements of the group to indicate moves to adjacent cells and respects the structure of the spacetime. That means that you have different recurrence lengths along the time and space dimensions. So let's look at this a little bit more carefully. So a spacetime is a continuous thing. It's got continuous spatial and time directions, and the chromatic group of the space-time, it's a finite group that kind of generates it, and it has an odd number of elements, one of which is the identity element. So you have the identity element, and then you have an even number of elements. And the idea is that all of the elements that are not the identity element correspond to a direction that you can move in the space-time, either a time direction or a space direction. And if you move along the space direction, then if you move along a space direction, then after a while it will repeat, because it's a finite group, so the labels that are assigned to each of the cells in space will eventually repeat. And if you move along a time dimension, it will also repeat. But in order for the chromatic group to respect the space-time structure, if you move along a time direction, the number of steps that you go before it repeats has to be different to the number of steps that you go along in a space direction before it repeats. So you can think of a chromatic group as kind of the group of movements that you can make in the space, the group of one-step movements that you can make along different directions in the space or the space-time. So let's have a look at an example. So this is one-dimensional space. This is just a line, and the chromatic group is Z3, the cyclic group of order 3, and the elements of it are 0, 1, and 2. So you can see that this generates a labeling of space-time, or of one-dimensional space, and it has the characteristic that if you're in any of those cells, then you know which cell is to the left of you, which cell is to the right of you. There are different numbers in the cell to the left of you and the cell to the right of you. And that means that you can distinguish left from right, which is what you want to do if you're in one-dimensional space. So we'll have a look at two-dimensional space. So this is the plane, and the chromatic group of the plane is Z5. So this is the integers mod 5, 0, 1, 2, 3, and 4. And as you can see, if you look at this grid here, if you keep going down, then it goes through a sequence 1, 2, 3, 4, 0, 1, 2, 3, 4, 0. And if you move to the right, it goes 0, 2, 4, 1, 3, 0, and so on. So what it does is it has a repeating sequence that it repeats after, it has a recurrence length of 5 in each direction, and the different directions correspond to adding different elements of the cyclic group. So for example, if you move right, that's in this diagram here, that's like adding a 2 to the number that's in the cell. If you move to the left, it's like adding a 3 or subtracting a 2. If you move down, it corresponds to adding 1. And if you move up, it corresponds to subtracting 1 or adding 4. So that's the chromatic group of the plane, which is Z5. And we can look at more chromatic groups here. So this is a collection of different spacetimes and the chromatic group associated with each of those spacetimes. So you can see that for 1D space, 2D space, and 3D space, it's pretty simple. The chromatic group is just it's the cyclic group whose order is twice the number of dimensions plus 1. So it's Z3 for one-dimensional space, Z5 for two-dimensional space, and Z7 for three-dimensional space. But for four-dimensional space, it's actually a product group. It's not the simple, it doesn't continue with the same pattern that you see for 1, 2, and 3 dimensions. It's a product group of the cyclic group with order 3 multiplied by itself, so 2 copies of Z3. And we can explain why that is later on. And for 1 plus 1 dimensional spacetime, 2 plus 1 dimensional spacetime, there is no chromatic group. Those spacetimes don't have a chromatic group that labels them in this kind of a systematic way. And with 3 plus 1 dimensional spacetime, the chromatic group is Z9, the integer is mod 9, and that's essentially why mod 9 is special, because it's the chromatic group that corresponds to 3 plus 1 dimensional spacetime, and 3 plus 1 dimensional spacetime is the spacetime that we live in. So these are some characteristics of chromatic groups. Each chromatic group generates a unique space and spacetime, and each space or spacetime has at most 1 chromatic group. And many spacetimes, for example, 2 plus 1 dimensional spacetime, have no chromatic group at all, and the chromatic group of the spacetime we live in is Z9. So we can just take that definition and plug it into an AI and ask it to identify the chromatic group of 3 + 1 dimensional spacetime, and you can see it gets the right answer. And the point of putting this in here is just to show that the definition is sufficient, it is clear, it does specify a unique chromatic groups for the various spacetimes, and an AI can tell you that the chromatic group of our spacetime is the cyclic group of order 9, and it doesn't need any further information apart from the definition. Okay, so this is why Z9 generates 3 + 1 dimensional spacetime and not 4-dimensional space. If you move in the 1, 2, 4, 5, 7, or 8 directions in mod 9, then you get a sequence that repeats after 9 digits. So if you keep adding 2, you get the sequence 0, 2, 4, 6, 8, 1, 3, 5, 7, 0. And if you move into 3 direction, it goes through the sequence 0, 3, 6, 0. So it repeats after 3 steps in the 3 or 6 directions, but it takes 9 steps to repeat if you move in any of the other directions. So this means that you get 3 spatial dimensions. So the 1, 8 axis, so you can move right or left you can move right by adding 1, you can move left by adding 8. The 2, 7 axis, the 4, 5 axis, and then there's a time dimension, which is the 3, 6 axis, which is distinguished from the spatial dimensions because it has a different recurrence length. And that's why Z9 respects the space-time structure of 3 + 1 dimensional space-time rather than 4-dimensional space. Okay, so why should we care? You could look at chromatic groups, you can say, okay, each spacetime has a chromatic group, but why do I care about that? And the reason why it's interesting is because if you have a field, something like a voltage, anything at all, that depends on space and time coordinates, and it's a local field. So this is a nearest neighbor field, which means that the value of a field in a particular cell in space-time depends only on the values of the cells, the values of the field in the cells that are immediately adjacent to it. And if the dynamics doesn't depend on the actual position in space, then you can use the chromatic group rather than the whole space-time to describe the dynamics of the field. So, for example, in 3 + 1 dimensions, we have these are the elements of the group. 0 is the identity element, and each of the other elements corresponds to moving in a specific direction in space or time. And if you do this, then you can write the equation that governs the field in this way. You can say that the next value of the field, if you have the field at a particular cell, then the value of the field in the cell, which is 1 time step after that, can be expressed as some kind of a combination of the values of the field in the previous cell, the here cell, the cell before that, the previous cell, the cell to the left of it, the cell to the right of it, and so on. So some combination of those other field values. It could be a linear equation, maybe it's even nonlinear, but if there is some equation that governs the field, then it can be written in a local form like this, and this means that you're not plugging space and time coordinates into the field, that you can just specify it in terms of the chromatic group, or the values of the field evaluated kind of at the cells indicated by the elements of the chromatic group. And if you do this, then you get essentially the same field dynamics as you would get in the whole space, but you don't need to express it using space-time. And just to say that in this case, or in any case, the values of the field don't have to be elements of the chromatic group. They can be something else. They can be integers, numbers, real numbers, they can be linear operators, they can be anything. So this is just about the labeling of the space-time. It's not about in any way restricting the values of the field or trying to take the values of the field mod 9. But if we do use mod 9 for the field values, this is something interesting where mod 9 shows how special it is again. Then we can add in parity and we can construct this field here. And this is the Rodin number map that we talked about in the previous video. And you can see, well, you can't see here, but if you watch the original video, you can see that where we show the proof, OR satisfies the mod 9 Klein-Gordon equation, and 2dr plus OR-G, where D is the Dirac operator and G is a square root of -1 inside the Clifford-Algebra algebra, that satisfies the discrete mod 9 Dirac equation. So you have essentially bosons and fermions inside this very simple mod 9 system, and these are non-trivial solutions to relativistic wave equations. And that means that mod 9 arithmetic it not only describes the 3+1D, the structure of 3+1D spacetime, but it also incorporates principles of modern physics, such as relativity, bosons, and fermions. Okay, so just to address some criticisms that we'll probably hear again and again. The first one, people are going to say this is nothing new, but in fact, I think it is something new. So mod 9 arithmetic, it describes the structure of the space-time that we live in, and it incorporates principles of modern physics, such as relativity, bosons, and fermions. And I didn't know that. If you knew that, then I guess it's not new to you, but I didn't know that, and I think nobody else did either. And so the criticism we'll hear is that mod 9 isn't special, and that's going to come from people who think that we're taking the values of the field mod 9 rather than using mod 9 to describe the structure of the space-time. So yes, it is actually special. It's the chromatic group of the world that we live in. And then people will say, so what? And you can say that to anything. But so yes, so what the results, or the reason that we're doing all this is that it shows that mod 9 arithmetic is kind of something that can give you some insights into physics. We didn't know that it had these structures that were compatible with modern physics. Now we do, and so it's worth trying to build on that. So I hope that clarifies things.